In this video, we are going to go through the pre-lab and kind of some introductory concepts and preparations for the empirical formula lab that we will be doing next week. Now, part of that lab is going to require you to do a little bit of advanced reading on calculations involving moles. And so I'm going to link a video that I made in the past to this video that goes over how to do those types of calculations. And so if you have trouble with kind of the concept itself of doing these conversions involving moles, I would strongly encourage you to go ahead and watch that video and stop this video and go back and watch that one first, because it won't make as much sense to see what we're doing here if you don't have that fundamental kind of background to draw upon. But assuming that you do, going ahead and looking at what is coming up, we can see that the lab that we are doing is the determination of an empirical formula. And so we are going to be looking at a couple of those fundamental laws of chemistry. In particular, we're looking at the law of conservation of mass. Mass cannot be created or destroyed, and the law of definite proportions, the one that says that when chemicals are brought into combination with each other, the compounds that they make are always going to be fixed whole number ratios of one element to the other, and that those fixed whole number ratios are going to be consistent. But we also need to be aware of the law of multiple proportions, which says that if we play with the starting amounts too much, we can actually form different compounds as a result. And so we're going to test that in this particular lab by combining copper and sulfur together. And in combining that copper and sulfur together, we are either going to get the copper 1 sulfide, Cu2s, or the copper 2 sulfide, Cus. So the concept that really is at play here is the concept of the mole. And so rather than doing empirical formulas kind of in the way that a lot of textbooks are going to look at it, where we start with mass percentages and we turn those percentages into masses and we turn masses into moles and we do a comparison, we're going to do things a little bit differently. Since we're actually doing this experiment in lab, we're going to have masses for those elements in that lab. And so we can do the mass to mole calculation right away, which is why it's really important that you look at that mole concept and understand it as fully as you can before you go out and try to do these calculations. So we've given you a sample calculation to kind of show you what you need to do in this upcoming pre-lab. And so we're told that 0.3268 grams of vanadium is mixed with 1.12 grams of sulfur, and the sulfur is in excess, meaning there's way more sulfur present than what can react with the vanadium. We are told that the product is 0.8389 grams. And so that becomes our starting mass here in calculation A. And calculation B asks for the starting amount of vanadium, which again, we measured directly there. So the first thing that we need to do is we need to do a direct conversion between the grams of vanadium to moles of vanadium. And for that, we're going to need the molar mass of vanadium to properly do that conversion. And so this sets up very similarly to the kinds of unit conversions that we did in chapter 1, where we have a unit that we're trying to get rid of here. Here in grams. Grams is in the numerator here. We move it to the denominator here in our conversion factor. The grams end up canceling out. And we have left moles of vanadium as a result. Now, one thing that you'll notice in these kinds of calculations, we usually tend to carry more significant figures. And that's because to do this kind of analysis the most precisely and the most accurately, you usually have to use some more precise instrumentation. And so in the laboratory, we will actually be using analytical balances, which read to 4 decimal places, as opposed to the normal centigram balances, which only read to 2 decimal places. Those extra 2 decimal places are going to create for us 2 additional significant figures, which will help us to eliminate rounding errors as they come up. Now, if we follow the logic here for letter D, our product contained vanadium and sulfur, a vanadium sulfide product. We know the mass of the vanadium because the law of conservation of matter tells us that matter can't be created or destroyed. So all of the vanadium that started the reaction has to be there at the end of the reaction. And so if we do the subtraction here, the difference between letter A and letter B is how much sulfur actually reacted. And so this is where we get our 0.5101 grams of sulfur. So we're going to do the same thing now to the mass of sulfur that we did to the mass of vanadium. Set up a dimensional analysis using the molar mass of the sulfur and cancel that out to get the moles of sulfur. And so now we have moles of vanadium and we have moles of sulfur. To turn this into a chemical formula, we're going to need to take these decimal values here and turn them into like whole numbers. Now, the only way that we can do that is by making sure that we get some whole numbers. And the way we do that is we always divide both of these numbers by the smaller of the 2. So we're going to divide both of these numbers by 6.415 times 10 to the negative 3rd. And if we do it to both of them, then it basically evens out. And so how it evens out now is I have 1 mole of vanadium because number divided by itself is 1. And if I do the calculation, I end up getting 2.48, which we're going to round to 2.5, which means that we have 2.5 moles of sulfur. Now, those are not whole numbers either, but they're a heck of a lot closer. And so one of the consequences that comes out of this particular technique is by doing the division, we always guarantee that we're going to have 1 whole number because the number divided by itself will always give us 1. What happens with the other number or other numbers is that they either turn into whole numbers themselves or they end up being fractions that we can easily recognize. And by fractions that we can easily recognize, we're talking about things like 0.25, 0.50, 0.33, 0.66, 0.75. Now, to get rid of these, we have to recognize that all of these are fractions, and to get rid of them, we need to multiply by the denominator of their corresponding fraction. So the quarters, 0.25 and 0.75, we'd multiply those by 4 to get rid of the quarter. For the 0.33 and the 0.66, those are thirds, so we're going to multiply those by 3. For the half, denominator's 2, so we're going to multiply that there by 2. So in this case, we have a half. So we know we need to multiply it by 2 to get rid of the half. Anything that we do to the one, we have to do to the other as well. So we went from 1 vanadium and 2.5 sulfurs to 2 moles of vanadium and 5 moles of sulfur. Now that I have both of these as whole numbers, I can turn them into an actual chemical formula, V2S5. Before this point, I couldn't do that because I either had funky looking decimals or fractions. And so this is the empirical formula, and this is going to be the base for what we are trying to do in lab. We're going to take copper and sulfur, we're going to react them with each other, we're going to take the mass of the products, the mass of the reactants, and we're going to try to figure out how much reacted and what's left over in that crucible after the reaction has commenced and after it is finished. These last other calculations here, G, H, I, and J, these are all ways to kind of test how well we did in terms of making our product. And so letter G is all about percents. So we're looking at what is the percent metal, or in this case, the percent vanadium in our product. So I take the mass of our vanadium divided by the total mass of the product, and I get a value here, 39.05%. So this is based on experimental data. In letter H, we're going to take the molar mass of the V2S5. So this is going to create for us the basis of our theoretical yield, our theoretical percent. Where that comes in is looking at the formula. We had 2 vanadium atoms, so that's why we multiplied the molar mass of vanadium by 2. And the total mass of 262.18 goes here. And so we can see that experimentally we got 39.05% vanadium. Theoretically, it should have only been 38.86%. So there is a slight difference between the two. That's okay. That's real. That's normal. Calculate the percent error by taking the difference and dividing by the theoretical number. We end up getting a percent error of 0.49%, which is fantastic for a technique like this. Anything below 1% really is absolutely great for this kind of lab. So this is what you're being asked to do in the pre-lab. And you can see that the pre-lab itself that you have is basically the same thing, only instead of vanadium and sulfur, you're dealing with iron and oxygen. So slightly different, but pretty much the same. So that's the pre-lab for this particular lab. I wanted to take one extra minute here and talk about the actual analysis, the thing that you're going to do with this, and that is writing a formal lab report. Here in Lab Archives, you can see that there is a writing guide and a rubric for that formal report that you can open up. And so what we are looking for out of this formal report is there are going to be 11 sections. Those 11 sections include titles, purpose statements, theory, procedures, observations. And so under each one, we have some prompting questions, things that you should definitely include in your discussion, what we expect of you from each section, and then down here, this is the rubric that we are going to use to ultimately grade your submissions. And so you can see in here, we've got checklists. We also have different ways to evaluate each thing. We have a certain quality section here in terms of what was your percent error, how well did you do the analysis, does it make sense? And then there's an error analysis piece here. I'll be speaking more about this in lab on Thursday when we actually go to do this, but I wanted to kind of introduce you a little bit to it now because, again, you're going to be doing something that you probably haven't done before. And if you have, you may not have done it this way before. So I wanted to be sure that you're ready and that you knew this isn't going to be like your other reports where you just fill in the data tables, hit submit, and you're done. You're still going to fill in the data tables and do the calculations and hit submit. But then there's a whole other assignment that comes in after that. And so you need to be aware that your work is not done when you leave lab that day. So that's all for this particular video. Once again, I'm going to relay you to that video on the mole concept, just in case you have a little bit of difficulty or you just want a refresher for it. It's a nice 20-minute video that really goes through a couple of examples of calculations to lead us to kind of the theoretical basis for what you're doing in lab. So until next time, take care. I'll see you in lab.